Hi everyone, welcome to your lesson 6 from Unit 1 notes. Hopefully we can get through our transformation of functions with no technical snafus. I'm hiding out in the third floor of my house away from everyone, so hopefully there's quiet. Though I have heard a woodpecker, I think, pecking on my house, so you may hear some tap tap taps. We'll see. Anyways, hello. So, welcome back to week 3, transformations of functions. Hopefully you went through your notes of all the different types of parent graphs that we could potentially foresee throughout this course, but you really will see when you get to calculus. So let's go ahead and just jump right to it. So the simplest form in a set of functions that form a family, namely f of x is equal to a times your function of x minus h plus k, is commonly called the parent function. A change made to at least one of the values a, h, and k is called a transformation. So you have 4 different types of transformations that could potentially occur. And if you guys remember back to your geometry day, you probably went through all these different types of transformations. I'm going to give myself some space to write. The first one we have potentially that could happen is what we call a dilation. We could have a reflection. We could have a rotation. Or we could have a translation. Now, the most common ones that we're going to be probably using are the reflection and the translation, because those are going to be the ones that are most commonly seen in the mathematical world. Okay, so we have what we call 2 different types of transformations that can happen. We have the rigid transformation and we have non-rigid. So let's go ahead and discuss the rigid transformations first. Rigid transformations are transformations that keep the original shape and size of the graph unchanged. So if we go through all the different things that could potentially happen, let's see represent any type of real number. If we were to do our f of x and then, so our function, and then add c, that would mean that we would be going up c units. So if we think about that as an ordered pair, I would have my x coordinate staying unchanged, and my y coordinate would have a plus c being added to it. Okay. For f of x is equal to, or y is equal to f of x minus c. I'm just trying to organize my stuff here. My notes. That means we're going to take it down c units. So my x again is unchanged, but my y, we would be subtracting c from all of those. Okay, so that's when our plus and minus c is on the outside, not directly affecting the x. The next 2 scenarios, we have the c actually connecting and affecting the x directly. So when we have x minus c, that means we're going to be moving to the right c units. So we would be taking our x and we would be adding c to it each time. Our y now is unchanged. When we have our function and we're going to add c to x, that really shifts us to the left c units, which means we will be doing x minus c and our y is unchanged. Taking the absolute value of y. So whenever we take the absolute value of y, this is when we are going to reflect any negative y values, which ultimately means that we're going to end up doing something above the y-axis, right? Or not the y-axis, the x-axis, sorry. because you're going to be taking all of those negatives and then flipping them up. So you're flipping them over, reflecting them over the x-axis. So our rule would be, we would have our x values and we would take the absolute value of whatever our y values are. Sometimes we can end up with taking the negative of our function, and this means that we would reflect it across or about. You'll sometimes see the word the x-axis. So we're taking the negative of our y, and then taking the negative of our x makes us reflect across or about or at the y-axis, which means we're taking the negative of all of our x's and our y's go unchanged. Okay, so those are all the different types of rigid transformations that are going to be occurring. Hopefully you already have the first 4 potentially in your toolkit in your brain and remember those from previous classes. Maybe we didn't quite remember our reflections over the x and the y axis, but you want to make sure that you have those down. Okay, so now let's go to our non-rigid transformations. Non-rigid transformations is when you're going to distort the shape of your graph. So these are your stretch and shrinks. So are we stretching it out? Are we shrinking it up? What are we doing? We're actually stretching it out, shrinking it up. Stretching makes it goes taller. So for the first one we have, what happens when we have our c be a factor in front of our f of x? Well, when your c is a number larger than 1, because if it was 1, nothing would change. So when it's larger than 1, we're going to be doing a stretch. It's going to be stretching it by a factor of c. So my rule would be x goes unchanged, but my y gets multiplied by that factor of c. Okay. When that c is a fraction between 0 and 1, then it's going to be a shrink. So it shrinks it by x comma cy. So if you think about it, multiplying by a number between 0 and 1 would definitely make your y smaller, right? Okay, and then the next 2 are your horizontal. So these two were our vertical. So these were vertical. Let's see, can I write up? Yep, just spin my iPad. So these are our vertical stretches and shrinks. And then these bottom 2 are our horizontal stretches and shrinks. Okay, so for when we have it being affected to the actual x, so when we're multiplying or taking that scalar of c and multiplying it directly to the x, it's going to be shrinking. So it's going to actually end up being a shrink here. It's going to shrink our graph, or your graph. Let's just put shrinks the graph by a factor of 1 over c. So our rule would be that we would take our x, divide by c, y goes unchanged. Okay, so the same rule is going to apply even when our c is in between 0 and 1, but now let's think about this. If I were to divide by a fraction, right? So if I were to divide by 1/2, isn't that the same as multiplying by 2? So actually it would make it get larger. So this actually ends up being a stretch by a factor of 1 over c. Because if you think about it, if we were to multiply by a fraction, it really would end up probably making it a larger number. Oops. Okay, so there are our non-rigid transformations, which are your stretch and your shrinks. Okay, when we stretch or shrink to the vertical, it's going to be going up. Horizontal kind of compresses it down. Sometimes I think about it as a compression. So now, can we use all of these different types of transformations in context with parent graphs? So here we go. Example number 1. Use the parent functions from our previous lesson to describe how the graphs of each of the following functions will be transformed. State the types of transformations and graph the function. Okay, so here is our first function. To me, right now I see that squared, which tells me that my parent graph was probably, or is, not probably, is f of x equals x squared. So it's going to be a quadratic graph. Remember, your quadratic graphs are your parabolas. Its vertex, minimum point is down there at 0, 0, and then it's concave up, right? So now let's see what we've got going. Well, I've got a -2 happening inside. So that means we're going to be doing a shift to the right 2 units. I've got a +4 happening here, which means we're going to go up 4 units. And then we have a negative occurring to the whole entire function, which means we're going to reflect about the x-axis. Okay, so starting with my original ordered pair of my vertex at 0, 0, we're going to now go over to 2, 4 for my minimum, or my vertex of my parabola. Normally it would probably end up looking like that, but it's not. We're actually going to end up reflecting it going down. So now if you guys remember from the last lesson, the pattern for parabolas is up 1 over 1, then we go up 3 over 1, then we go up 5 over 1. Remember that rule? So instead of going up, we're going to go down 1 over 1, reflect it, go down 1, 2, 3 more over 1, down 1, 2, 3. We can go down 1, 2, 3, 4, 5 over 1, 1, 2, 3, 4, 5 over 1, and we can keep doing that as long as we want it to, but that looks about right. So then here is our graph, and then I am going to label this as our f of x function. Okay. Label important ordered pairs. Here we're at 2, 4. It's always good to order or label your intercepts. We've got an intercept at 0, 0. I have an intercept at 4, 0. Cool. All right, let's jump over to B. So B, I see a +3 happening inside, which means that we're going to shift to the left 3 units. I see a -5, which means we're going to go down 5. And then I have that 2 in front, so my A is equal to 2, which means that we're going to stretch it. Right? Get rid of the little dot there. So it means we're going to be stretching it. So if we remember again, if it's in front and we're stretching it, what's happening to my y's? We're multiplying all of my y's by 2. Okay, so absolute value, remember, is a v. Original parent graph absolute value starts at 0, 0. So now my new vertex is at 3, -5. Or no, sorry, -3, left -5. Puts me right there. Okay, and whenever you're doing absolute value, really your slope is the same as that A in front. So really we're just kind of going up 2 over 1, up 2 over 1, and it just stays consistent because it is just the linear graph reflected over. So up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. Do the same thing to the other side, up 2 to the left, to the left, to the left. Now I ran out of space. So let's go ahead and connect those. That is my g of x function, so I'm going to label it as such. Let's label important parts. My y-intercept is at 0, 1. It's kind of hard to see what that x-intercept is, so I'm just going to leave that blank for now. Down here, we will be able to find what that is eventually, right? -3, -5 is my vertex. Any other nice points? No. Okay. Okay, so now let's go ahead and move on to example C. Example C has us graphing the absolute value of 2 minus x minus 3. There we go. I got rid of that correctly. There we go. Maybe I'm back Not sure. I had to pause it for a second. We had an emergency. Okay, so we have h of x is equal to the square, or the square root of 2 minus x minus 3. The easiest one we notice right away is the minus 3. So that minus 3 means we're going to be going down 3. Then absolute value, that's kind of like a vinculum. That's a fancy word for grouping things together, a vessel that puts things together. So underneath it, I know with the 2 minus x kind of flips everything. So we have right 2 units, down 3, and then the negative in front of the x means that we're going to be changing the x, right? So taking the negative of that. So when we change the x and flip it over, that's going to be a reflection about the y-axis. Okay, so we're going to be going to the right 2, down 1, 2, 3. So there's my new vertex. And remember, our normal absolute value graph goes like this. Well, in this case, we're reflecting it over the y. Right? So now it's going to go like this. And just follow the same pattern. So when we have a parent graph, it's up 1 over 1 for our first. Now I'm going to go backwards up to the left. And then if you think about your normal parent graph, your next would be 4, and then 2 would be your nicest one, right? So if I do this, let's do this in a different color. So we have 0, 0, 1, 1, and then 4, 2. So we're going up 1 over 1, 2, 3. So if I do the same thing with the purple, going up 1 over 1, 2, 3, that would put us here, right? And if I think about it, plugging in negative 2 would get me 4. The square root of 4 is 2. 2 minus 3 is negative 1. And there would be our h of x graph. So let's go ahead and label h of x. My vertex is at 2, negative 3, and it's hard to tell what my y-intercept is, or what my vertex would be either, or my, not vertex, my x-intercept. Okay. All right, let's jump over to D. D is a cubic. So remember, our cubic graphs look like this. Right, normal behavior is right there. I have a minus 3 happening inside, so that means we're going to be moving to the right 3. We have an up 2, and then we're going to have a vertical, because our scale factor is on the outside, a vertical shrink at 1/2, and then we're going to have a reflection about the y, or the x-axis, right? Because we're taking the negative of our y's, which means we would reflect it over the x-axis. Okay, so right 3, up 2, so that puts me at 3, 2. So then for this one, probably the easiest way is just kind of doing some quick substitution in. If I substitute in the value of 1, we get 1 minus 3, which is negative 2. Negative 2 to the third is 8. Negative 1/2 times 8 is negative 4. Right? Sorry. Negative 8 times negative 1/2 is positive 4. Plus 2 is 6. 1, 6. And then if we do the same thing, let's say with 5. 5 minus 3 is 2. 2 to the third is 8. Negative 4 plus 2 is negative 2. So we have our graph kind of looking like this. All right. Okay, so hopefully we did okay with those. You know, if all else fails, pick some values, make a table of values, and see what it looks like. All right. Okay, so example 2 has us using a graphing utility to explore the transformations of the following graphs, and then we'll explain the transformations that are occurring there. So let me go ahead and get my graphing calculator turned on. Remember that your original is x squared is our quadratic graph, so a parabola. And then we're going to explain the 3 different transformations that can be happening. While I'm waiting for my graphing calculator to get started, let's go ahead and do the original, right? Because that one's easy to do. So x squared, 0, 0, 1, 1, 2, 4, 3, 9, which gets me negative 3, 9. 4, 16, we got space on this graph for that, so 4, 16, which makes me have a negative 4, 16. All right, so in purple I have my original f of x function. So f of x equals x squared. There it is. Okay, so now what we're going to do is 2 of x and then 1/2 of x. So let me get this open here, clear out of my stats world. Quit. Oh, I'm going to do this. Yes. Quit. Here we go. Yes. All right, so now in our y equals screen, we have our original, which was x squared. And the cool thing about my calculator is it's going to do everything in different colors. Yours may do that. Yours may not. The next one was 2x. So 2 times my x. And then my next one is 1/2. We'll be lazy and just use 0.5 x and enter. Make sure my stat plots are turned off so that we don't have some confusion going on. All right, so here are our 3 different graphs. Oh goodness, where'd that stuff come in? I forgot my x squareds. X squared, there we go, and 1/2 x squared. Okay, so now when I go back to my graph, original, then we have the 2x, and then we have the 1/2 in black. So does everybody see how the original was the blue? When we went from blue to red, you see how it kind of, either it stretched it, right? It made it get a little bit tighter. So you think about like stretching its arms. You guys are probably too young to remember Stretch Armstrong. But you'd stretch them out so it would get them skinnier. And then your shrink, I kind of think about as a compression going down, is the black. So it gets a little bit wider out. So let's go ahead and recreate these graphs back onto this graph. So I had my original in purple. I'm going to make my 2x red because I can. So whenever we're doing the f of 2x, okay, we're dividing. So that's directly happening to the x. So it's going to be a horizontal stretch with a factor of 1/c. So our rule is going to be x divided by 2 comma y, right? And we're doing 2x squared. So if I plug in that 2x into my f of x, 2x ends up being 4x squared, right? So if we think about our original numbers, 0, 0 stays the same. My coordinate for my purple at 1 was 1, 1. This was 2, 4. So if I plug 1, 1 into the red, the 2x, right? Well, I'm just taking half, so it'd be 1/2 comma 1. Which puts me 1/2 comma 1 here, right there, reflect it. If I do the same thing with 2, half of 2 is 1, so now my new point is 1, 4, right there, right? Up here we were at 3, 9, that one's going to be a little bit uglier, but let's go up to the 4, 16, because that's nicer, because I can take half 4 and get 2, so then we would be at 2, 16. All right, so there is our new graph. So that is f of 2x. I'm going to do a different color. Let's go green for our last one. So f of x, or f of 1/2 x, when we plug that in, we get 1/4 x squared when we plug that into our function, right? And then this is going to be a horizontal shrink. Horizontal shrink with our factor going to be at 1/1/2. So x over 1/2. Now remember, isn't that the same as just 2x? Right? Because multiplying by the reciprocal would get us 2x. So if we do that transformation again, 0, 0 stays. Now 1 becomes times 2, so 2 comma 1, reflect it. 2, 4, now it's going to become 4, 4, so 2, 3, 4, 4, reflect it. 2, 3, 4, 1, 2, 3, 4. Oops, doesn't like my fingers anymore, and it's going to look like such. Okay, so there we have the 3 different types of transformations happening with the explanations. All right. Example 3. So now we're going to get a graph that's going to be connected with just line segments. So not just a normal graph that we're used to. And then we're going to do the different transformations to it. So in the grid at the right, we're going to graph our normal f of x. So our first, and I think I need to move this down so I can actually see all the ordered pairs. Nope, keep me there. Let's make this smaller and I can get all of it on. Perfect. Okay, so we have our first order pair is at -4, -2. So -4, -2, graph it. Now we're at -2, +3. And I'm going to connect that with a straight line. Then we're going from to -1, 0. Connect. Then to 1, 4. Connect. And then to 4, 2. Connect. All right, so there is our function f of x. So now what we're going to do for part B is we're going to do this transformation to all of those ordered pairs and see what our new ordered pairs are going to be. Okay, so our first one, ordered pair, is at -4, -2. So what are we going to be doing to all of our x values? Well, we have a -3, which means we're shifting to the right. So that means I'm going to be adding 3 to all of my x values. I have a +4, which means we're going to be doing a +4 to all my y values. And I have a -2 in front of the function, so the -2 in front of the f of x -3. So I'm going to multiply everything by -2 first, then add 4. So there's our rule. So here we go. Let's do it. So -4 + 3 equals -1. -2 times -2 plus 4 gets us 8. So my ordered pair is -1, 8. Continuing, -2 + 3 equals 1. -2 times 3 plus 4 equals -2. So 1, -2. -1 + 3 equals 2. -2 times 0 plus 4 equals 4. So we get 2, 4. 1 + 3 equals 4. -2 times 4 plus 4 equals -4. So 4, -4. And then the last one, 4 + 3 equals 7. -2 times 2 plus 4 equals 0. So 7, 4. So now I'm going to graph that. The same graph, different color. I'm going to go with, let's go with blue. So -1, 8. It's up here. 1, -2. So 1, -2 is right here. So I'm going to connect those. Then we have 2, 4, which is right here. Connect those. 4, -4. Connect. And then 7, 0 is here. All right. So there's our graph. So you can kind of see how it's being reflected over the x-axis, right? Kind of see that reflection happening. And we have all the different shifts happening also. All right, so hopefully you're good to go with that one. Let's move to example 4. So this one's a bit lengthy. We have a few different variations to do of our square root graph. So again, when you get to calculus, it's really important to be able to, 1, identify what a parent graph would look like, and then 2, what would be happening to the parent graph based off of these different types of transformations. Okay, so we have here square root graph is our parent graph. So what's happening to our first one when we take the negative of the square root of x plus 2? So we have an up 2 going on, and we have a reflection about the x-axis, because the negative is not directly attached to the x, it's in front of it. Okay, so our normal parent graph is here, right? So I'm now going to shift it. So the red's going to be our final answer. I'm going to shift it up 2 units, right? And then I'm going to reflect it about the x-axis. So that means we're going down instead of over. So I'm going to go down 1 over 1, and I'm going to put this guy right here. So there is our graph. Do some labeling, 0, 2. I nicely can see my x-intercept is at 4, 0. Okay, so my final answer would just be the red. I just put the blue on there so we can kind of remember what that looks like. So let's get rid of that. There we go. Domain, we're going inclusive with 0 to infinity. All right, B has us actually taking the negative of our x. So that means we're going to be doing a reflection about the y-axis. Okay, so again, think about our normal graph. It's this way. So if I were to reflect that, 0, 0 would stay there. Our new point would be at -1, 1, and our other new point would be at -4, 2. So that left side would be the correct answer. What's the domain of that? Well, we're going to negative infinity to 0 inclusive. And then for the last one, we have the negative in front, which means we're going to reflect on the x-axis. And we have a +2, which means we're going to move to the left 2 units. So we're going to the left 2, and we're reflecting down. So now we're going to go down 3, 1, 2, 3. There we go. Some important points. We got -2, 0. Kind of hard to see what my y-intercept is, so I'll just leave it blank. Okay, so those were rigid transformations. You know, the graph did not stretch or shrink. They just translate it and reflect it. All right. Example 5 is our last one. So we're going back to our straight line segments connecting the graphs. I'm actually going to do the first two with you, and then you're going to do the last 4 on your own to see how you did with it. Okay, so we have the function g is continuous function that is defined on the closed interval from -3 to 3. Use the graph to complete the table of g. So looking at the graph, when x is -3, it looks like my y is at -3. When my x is at -2, we're at -2 also. At -1, we're at -1. At 0, we're at +1. At 1, we're at +1. At 2, we're at 3. And at 3, we're at 0. So everybody see where those ordered pairs come from? Okay, so now for part A, I'm going to make a quick table of values this way, just because that's where I have space. We're going to be taking the absolute value of our x and then plugging it back in. So we're doing our x values, and then we're going to figure out what my new output would be with the absolute value of that x. So my x's are not changing. So -3, -2, -1, 0, 1, 2, and 3. So now what happens? So when I take the absolute value of -3, I get 3. So now go back up to that table. When we have a +3, what's my output? 0. At -2, the absolute value of that is +2. Go back up to the table. When we have a 2 as our input, what's our output? 3. Do the same thing with -1. Absolute value of -1 is 1. Output at 1 is 1. Absolute value of 0 is 0. Output is 1. Absolute value of 1 is 1. Output is 1. Absolute value of 2 is 2. Output is 3. Absolute value of 3 is 3. Output is 0. So now we can graph that, and we get -3, 0, -2, 3, -1, 1, 0, 1, 1, 1, 2, 3, 3, 0. Connect, connect, connect. It looks kind of like Batman ears, huh? Anybody dressing up as Batman for Halloween? Probably not. All right, and then for B, now we're going to be taking the absolute value. So our rule here is we're taking our x, and then we're taking the absolute value of y, right? Over here, our rule was take the absolute value of our x to get our y. So my x's are -3, -2, -1, 0, 1, 2, 3. So now at -3, the output is -3, but we're going to take the absolute value of that, which gets us 3. So I'm just taking the absolute value of all my y's. So now we have a +2, +1, 1, 1, 3, 0. So -3, 3, -2, 2, -1, 1, 0, 1, 1, 1, 2, 3, 3, 0. And here is our graph. Okay, so I'm going to have you pause this video, and I want you to do the next 4 all by yourself, and then once you have those completed, come back and check to see if you did them correctly. So pause it. All right, I paused myself so I get the answers up here really quickly. Check your answers with what I have here. I think I'm recording. Sorry, I'm getting stuck with my technology. Okay, so for C, we were taking the negative of all our x's, and the y's were not changing. For D, you were taking a scalar of 1/2, and remember that's just the same as just doubling. Okay, so doubling your x, so I took all my x's and times it by 2. My y's were unchanged. For E, with a scalar of 2 means we're going to do 1 over our C, so 1/2 of all of our x's. Right, so you can kind of see that shrink happening there. So E was a horizontal shrink, D was a horizontal stretch, and then for F, we were just shifting the whole thing over to the right 1 unit. So I shifted all of my x's to the right one, but my y's were unchanged. So hopefully you were able to get those. Now you may move on to your next assignment.